So hello and welcome. So today we are going to have additional examples on flexural stress applied not only on beams but in structural members that are subjected to couples or bending. So starting with this first problem, we have a flat steel bar. The cross section are given as well as the length of this flat bar, and it is being bent by couples applied at the ends so that the midpoint deflection is 1 inches or 1 inch. Compute the stress in the bar and the magnitude of the couples. Use E, or the modulus of elasticity, equal to 29 times 10 raised to 6 pounds per square inches. So if we are going to illustrate the problem, we can illustrate the figure by its dimension here. So it is 40 inches long. So say this is the cross-sectional area. We have the dimensions on it. We have the thickness to be 1/4 of inch and a width of 1 inch. Couples here will be applied on the far end of both ends of this flat bar so that it will cause a 1 inch deflection at the midpoint of this flat bar. So basically, as we can see here, there is a radius of curvature because this was bent on both ends, causing this deformation at the mid span. And there will be a point of origin for that radius of curvature. So here are those radius denoted by rho, and this is also rho here. Okay, so we would like to utilize those dimensions in order to come up with the couple as well as the bending stress. So in our derivation last time, we have an equation, a general equation on the bending moment and relating it to the flexural stress. And it is actually in terms of this equation. We have M over I, flexural stress over Y, is equal to E all over rho. So what is useful here, basing on the given, is to pair first these two sides of the equation so that we can solve for our moment couple applied. Say our moment is equal to EI all over rho. So we have the value for E. We can calculate I. And it is simply equal to BH cubed all over 12. So we have the base to be 1. Okay, so our height here is 1/4, or that could be written as 0.25 raised to 3 and then divide it by 12. So we can obtain the value of I here. We have an I of 1.3 times 10 raised to negative 3 inches raised to 4. So we put a check mark on E because that is already given. And we have already obtained our A. So now we are going to calculate the rho here. So we would want to utilize this right triangle here. And the base is just the half of 40. We have 20 each of the right triangle. And we use this dimension for the height of this triangle. That is actually the difference between rho and 1 inch, 1 inch. And then we could now write the Pythagorean theorem. We have rho as our hypotenuse is equal to the sum of its legs. So we have that as our expression. So simplify. We have 20 squared is equal to 400. And then expand that expression so that this is cancelled. We can combine that two and transpose this to the other side of the equation. So we have here 2 rho is equal to 401. So we can now solve for the rho. And that would be equal to 200.5 inches. So all we need are obtained. So we are going to substitute. So the value for E is this one, 29 times 10 raised to 6 times the obtained I divided by 200.5 as our radius of curvature. So we have 188.03 pounds inches. So upon obtaining our applied couple here, so we are now ready to determine its flexural stress. So, and of course it will involve now this equation, the side of that equation. So we're going to equate that by, I think it is much convenient, any, or we can just use this one or that one. Okay, so I'll just have here m all over I. So we're going to carry that equation and equate it by that expression. So y here is the half of 1/4, and that is actually 0.125. So we move further and then we substitute values. Then we have the flexural stress. DAM. Nakisamot ba dyan?
Doon sir. So pinag-aawang ka niya sir.
Ganito niya.
Doon sir, galing ka mo. Yun, kayo lang malima sir, may pag-PPDS kaya may habol. Mismo.
Okay. Ay, good afternoon, sir.
Sa Ronjon, iti atay niya pa niya iti office regarding iti overload.
Ay, well, sir.
Nagtungtong kami kini Madam Joy, it ko na si kayo nga iti mag-denti certification, tapos isang PQG office na.
Ay,
Ngayon magtakita dito so di nagtutungtungan kaya iti.
ay, kasi, sir.
So, mabalit, paalam lang ka dito documents dito
Oo. Well, sir.
So,
Sige,
okay
sir,
na.
sir. Okay, sige, sir. Thank you. Thank you, sir. Ikakano alam, Jeko? Jenny overload. Kay pull out ang kano ang magna kanya na.
Di masusunod eh.
Hmm.
Nagtutok kayo, sir.
Hmm.
Sir,
Ha?
Ang PDF, sir, talaga. Bakit JPEG? Nakakatagal yung file, sir, din sa Jonah. Sa Jonah ito.
Hmm.
Ano po ito natin?
JPEG kaya data. I-print screen mo nga eh.
BBS.
Save as mo nga ta. Ipan mo ti paint. Pan mo ti paint, i-crop mo.
Dito sa ito. Dito sa ito. Hindi naman po siya ikabalon siya. Dahil naman, di ba na kami? Di naman PBS. Bukas po ito rin mo.
Hmm.
Di, kung sa, designation mo, dito ba sa na kami? Hindi naman din mga PBS.
Sige.
Post ko na sir.
Mm.
Okay. Kung nag-ikat ko nag-ikat sir.
Hmm.
Iyak ko na mga pwede.
Korea.
Okay, makapasok mo nila doon.
Hmm. Sige.
Mag-take out sir, kung nag-ikat ko ha.
Hmm. we have 0.14 millimeters. And of course, on the basis that we substitute x here, which is 45 millimeters. And as for the stress, we'll just use the Hooke's law, wherein the Young's modulus of elasticity is equal to stress all over strain. So strain is expressed in terms of delta. That is actually delta all over L. So remember that the length here considered is 200 millimeters. Okay, so it is within the original length of 200 millimeters. So basically, the strain here will just substitute delta all over 200. So finally, if we are concerned with this value, we'll just cross multiply that one and then replace your strain by this. We have this equation. Okay, so if we are concerned with the top, then we can just denote this expression in terms of delta at top, and delta at top is 0.1, wherein we're gonna use E. What is our E here? So it is assumed to have 70 gigapascal, or that is actually 70,000 megapascal. So we place it there with the delta on top. So 200 here is the original length. Therefore, flexural stress on top is 35 megapascal, wherein this is actually in tensile zone. And for the other one, we will use the same formula but consider the delta at the bottom. That is 0.14. So we replace that value and come up with the flexural stress on the compression. Okay, compression zone. So as we can see, we have here the stress at the maximum. Okay, maximum stress along the tensile zone and the maximum flexural stress along the compressive zone. So those are the approaches on this problem. So first you're gonna need to locate the neutral axis and then obtain the maximum distance of these zones up to the neutral axis. So that will be our basis in calculating the maximum flexural stress on top and bottom fibers. So that's it for this problem, and I hope you will be ready to exercises. So thank you for listening and good day.